All right, so in the last video we talked about what it means for a function to be continuous. So somewhat intuitively we would probably guess that if a function is not continuous at a point, that's when we would call it discontinuous. Okay, so that's really the simple definition of discontinuity, is just simply not being continuous. So let's look at the few different ways that a function can be discontinuous. We've talked about again in the last chapter, so hopefully this is a review and a bit redundant, but we want to kind of formalize things, and we also need to re-emphasize really important aspects of continuity here. So let's look at the different types of discontinuity that we might have. So first we have, remember, in order for a function to be continuous, we need to have the limit exists, the function value exists, and they're equal, right? All three of those things need to be true in order for a function to be continuous, which means if any one of them is not true, then the function is discontinuous. And we're going to look at the different implications of each of these being false. So let's start here with the first type of discontinuity is, well, what if the function value exists and the limit exists, but they are not equal to each other? So if the limit as x approaches c of f of x exists, but is not equal to f of c, then f has a removable discontinuity. So you can see here the function, as we get very close to 2, the function is approaching 5, right? We could say that pretty confidently, that the limit as x approaches 2 of f of x is 5. As we get close to 2, the function value gets closer and closer to 5, right? But the function value at 2 would be this point right here. That's f of 2 right there. So f of 2 is 10. And it's hopefully pretty obvious that 5 is not equal to 10. So since the limit exists and the function value exists, but they're not equal to each other, then we know it's discontinuous. And specifically, we see we have this kind of discontinuity that we call a removable discontinuity. Where they're called removable discontinuities, there's a note right here, because all we would need to do in order to cause the function to be continuous is take this point right here and move it down. And so we can do that. We could do that by force by just saying f of x equals whatever this curve is, and then have a separate piece, do a piecewise function where f is equal to this curve for any value except 2, and then the second piece would be at 2, the function value, we'll just call it 5 by force. Okay, but so anyhow, we could move that point and remove the discontinuity. That's why we call it a removable discontinuity. But we also call it a point discontinuity because it's the curve is continuous everywhere except for that single point, right? If I were able to just cover this up, pretend it's not there, blank it out, it would look like this curve is continuous, right? Just at that single point where it's discontinuous. So we saw holes in the last chapter. Those would be examples of point discontinuities or removable discontinuities as well. Okay, so again, we call it removable because we could simply take that point and just slide it down, and then we would have a continuous function again. So that's a removable discontinuity, when the limit exists and the function value exists, but they are not equal to each other. So the third criterion is missed. Another type of discontinuity that we talked about is a jump discontinuity. A jump discontinuity occurs. A jump discontinuity occurs when the following happens. Here in this case, the main key thing is that the limit doesn't exist in a particular way. The function value may or may not exist, but the limit doesn't exist, and it has to not exist in a particular way. That is to say, the left-hand limit and the right-hand limit are not equal to each other. Here we can see this would be the right-hand limit. Right here would be the upper value. This would be the left-hand limit, and they're obviously not equal to each other. In that case is when we have a jump discontinuity. And I've talked about Mario running along the curve here. If I'm Mario, I'm running along, and I have to jump to get to the next curve and keep going, right? So hopefully it's pretty intuitive why we call it a jump discontinuity. But again, the reason that happens algebraically is that the left and right hand limits are not equal to each other, right? They may or may not both exist, but they're not equal to each other. Also, again, to emphasize, this is unaffected by whether or not the function value exists, right? In this left case here, the function value is on the left curve. But if that had been an open dot, we would still be in the same situation. Mario still has to jump to go from one curve to the next, whether or not that dot's open or closed. And over here, we see the dot could be somewhere else. Maybe it's not on either curve. It's in some other third point, or third y value. But any of those possibilities could be there. With or without that function value, we would still have a jump discontinuity if the left and the right-hand limits are not equal to each other. And then the last kind of discontinuity that we need to talk about is an infinite discontinuity. And the idea here is basically on one side or the other or both, the function is running up to infinity or down to negative infinity, right? So we say f has an infinite discontinuity at x equals c if one or both of the one-sided limits is infinite. So like we look at a here, the left-hand limit, right? I could say the left-hand limit, the limit as x approaches 2 from the left of f of x, well, clearly it's going, as you get close to 2, it's going to go whoop, run right up to infinity, right? So we would say that the left-hand limit is positive infinity. The right-hand limit, we see the same thing happening. It's running up toward positive infinity. So we'd say the limit as x approaches 2 from the right is also positive infinity. In this middle one, we can see that the limit as x approaches 2 from the left is going down toward negative infinity, and the limit as x approaches 2 from the right is going up toward positive infinity. Okay. And then in this last case, we see the limit as x approaches 2 from the left is actually a specific numerical value. It's 1. Okay. But the right-hand limit as x approaches 2 from the right is going up toward positive infinity. And as the definition says, if one or both of the left or right-hand limits is infinity, then there's an infinite discontinuity. So in all three of these cases, we have an infinite discontinuity. Even though in this one, this third option here, third example, the limit from the left side is a specific numerical value. The limit from the right side is infinite. And so if either one of them is infinite, that makes it an infinite discontinuity. So a lot of people might be tempted to say, oh, that's a jump discontinuity. But I would ask you, could Mario possibly jump high enough to get over top of this curve, right? This actually goes way up to infinity, well beyond any level he could possibly jump to. So that's kind of the key difference between a jump and an infinite. Is you could think of it sort of spatially that way, is if Mario's running along this curve, he can't possibly get to the top where he would be able to jump over to the next curve. Or down here, there's no way he could jump from infinitely low to infinitely high. So they're not jump discontinuities, they're infinite discontinuities. Okay, those are the three major types of discontinuities. In the homework tonight, you're going to practice a couple things. One, verifying that a function is continuous at a point. So you need to walk through that procedure that we talked about here, where you need to verify three things: that the function value exists, the limit exists, and that they are equal to each other, and explicitly show each of those three steps. Make tables of values to find your limits. And then you'll also be identifying discontinuities from graphs and looking at what kind of discontinuities happen when. So that'll be for practice tonight. That one's due this Friday. And then I'll continue on with the rest of the section in the next video.